Hi, welcome to this course on computational thermodynamics and kinetics of materials. As I told in the introduction video, this course will be a standalone one which will cover some basic thermodynamics, kinetics, and some physical metallurgy concepts. So those who are not from metallurgical or materials engineering background can also get benefited in the first few lectures. They can come on board. And also there is no prerequisite. So if you are just class 12, it's good enough to get into this course. So let us start with some basic physical metallurgy concepts. We will today cover microstructure, phase, and to understand phase better, we need to understand crystal structure and chemical composition. And we will see the scope of this course, which is microstructure prediction. What is a microstructure? So take an engineering component, for example, something like this. You cut into a small piece and put it into polymeric mold like this so that it is easier to polish it and prepare it to observe under microscope. Okay, so in the preparation part, there is an entire procedure called metallographic procedure, and there are volumes of books written on that. Put it under a microscope, you will be seeing a microstructure. It may look like this. This is all grains you see. All of them are in the same color, same shade of gray. Grain boundaries are darker. And these are also grains. You may observe something like this in a different material or in the same material which is processed differently. Here also you see two types of grains. One is brighter, one is darker. The left hand side is grains of one phase, and in the right hand side you see grains of two phases. Okay, these are a couple of differences in microstructures. It can also come something like this, grains of two phases you see here. The second phase morphology, the shape, we call it morphology. It is different here, kind of circular in shape, and it is more or less uniformly distributed. So this is a morphological difference compared to the second picture. Okay, so what are microstructural features? Grains, phases, one or more phases, grain sizes, their shapes and distributions. So why to study microstructure? What all these differences will bring? What is the effect of microstructural changes? They alter material properties. So that is really important. So material properties are affected by microstructure. If you know how to control the microstructure, you can control the material properties. So materials engineers usually bother about achieving certain good combination of properties for materials. Let's say good strength and ductility together, things like that. So in order to do that, one has to control the microstructure better. Okay. So in order to control the microstructure, you have to understand the microstructure well. You have to understand what is grains and phases. So to understand them, two important ideas are to be understood. That is crystal structure and chemical composition. So grain or crystal are same. So we will see about that in this slide. Let's bring that first picture that we saw, grains of one phase. Inside a grain, we have atoms arranged like this in a periodic manner. This entire periodic manner is essentially a repetition of a small structure, the one which is highlighted in black color here. So if you take that small part out, what you see is something like this. The atoms here are considered as some solid spheres. So if you take a cube out, the sphere is cut into 1/8 in the corners and 1/2 in the center of the faces. If you join other pieces like this, you get the repeated structure of the entire grain. Okay. So the center of all these atoms, if they are represented like this, okay, so these points are lattice points. Okay. So these lattice points where atoms sit, that entire structure is called unit cell. So crystal structure is defined like this. You have lattice points on which atoms are sitting. In some cases it can be molecules sitting. So lattice points plus atoms or molecules. This is called crystal structure. Okay. So grain or crystal has atoms arranged in it in a particular order called crystal structure. In a polycrystalline material, you will have multiple grains. So the picture that we saw before was a polycrystalline material. In that, atoms can be arranged like this. If it is single crystal within one grain, atoms will be arranged in one manner like this. So what is the difference here? If you see carefully, there is a orientation difference. Okay, if you follow a particular direction, it changes its orientation from one grain to the other grain. Okay, you can imagine this as the grain boundary. This is one grain, this is another grain. So between the grains, there is a change in the orientation. Right. So crystal orientation is different between the grains. That's the difference between different grains. If everything is one single phase, of course. Okay. So this is a polycrystalline material. There are some things called amorphous materials where there is no crystalline order. Atoms will be randomly arranged like this. For example, glasses, metallic glasses, the glasses that you see, they are basically looking like a solid, but inside there is no crystalline order. Okay, they are like liquids which are super cooled. That is how they are formally defined. It is more like a liquid which doesn't flow, extremely viscous liquid. That's how glasses should be understood. Okay, but there is no crystalline order. That is the important takeaway point about the amorphous materials. Right, let us come back to the unit cell that we saw, because most of the materials that we will be dealing with are crystalline in nature. This particular unit cell is at the heart of it. So if you see, an unit cell has these different lengths A, B, C, alpha, beta, gamma. These are the angles between the A, B, C. These 6 things together, A, B, C, alpha, beta and gamma, are called lattice parameters. Okay. So these lattice parameters vary so that different unit cells are possible, different crystal structures are possible for different materials. Okay, for example, a few of them are given here. So in the cube itself, we have simple cube, face centered cube, body centered cube. We have rhombohedral, we have tetragonal, we have hexagonal and so on. So these are different types of unit cells. So now that we have understood what is crystal structure to some extent, let us think about how to understand phases based on crystal structure. Okay. Consider this everyday example of ice and water. What is the crystal structure of a liquid? The water here, it has no crystal structure. And what about the crystal structure of ice? It is hexagonal. Okay, something like this here. Okay, so that is the crystal structure of ice. Now this is having 2 phases. Let us consider 2 phases in an alloy, something that we have seen already, a dark and bright phase. Okay, what kind of structures will be there in the dark phase and bright phase? For example, it may be FCC, face centered cubic, and body centered cubic. The white phase may be FCC, the black phase may be BCC, or they both may be same. For example, both may be BCC, but the lattice parameter, the A value may be different between them. Okay. So if 2 phases occur in a material, they can have different crystal structures for 2 phases such as BCC and FCC, or they can be having similar crystal structures with the different lattice parameters. For example, 2 phases BCC 1 and 2 with different A values. Right? So the takeaway point is this: in any case, different phases have different atomic arrangements. Okay, even if both are BCCs, their lattice parameters are different. So atomic arrangements are different essentially. So in any case, different phases have different atomic arrangements. That's about the crystal structure of phases. We told there is one more idea which is important to understand phases, that is chemical composition. Let us look at that. So chemical composition is the content of components in a material in terms of percentages or in terms of fractions. Okay. Let us consider water again. It's a phase. The chemical formula is H2O, which is saying that there are 2 hydrogen and 1 oxygen atoms to form this molecule. The components here are hydrogen and oxygen. Okay, the material is made up of these 2 components. So what is the chemical composition? So look at the definition. we have to find the content of components in terms of percentages or in terms of fractions, right? So these are the components. What is the percentage of hydrogen and oxygen? That's what we have to figure out. So the content of hydrogen is equal to 2 divided by 2 plus 1 multiplied by 100. What is this? 2 plus 1 is the total number of atoms, 2 hydrogen, 1 oxygen. It is in the denominator. Among that, 2 are hydrogen atoms. That is in the numerator. So this is going to give us a fraction 2 divided by 2 plus 1. That is good enough to express the composition of hydrogen, the hydrogen fraction. But multiplying that with 100 will give us a value in percentage, which is 67% or 0.67 fraction. Both are fine. So here we are counting the number of atoms. If you see 2 hydrogen, 1 oxygen, we are counting the number of atoms and using that to figure out the content of hydrogen. So the unit here should be atomic percentage. About the units we will see shortly in the next class. So more importantly, since components are only 2, express the composition with the content of only one component, that is 67% hydrogen. What do we mean here? We mean that if you express hydrogen content, automatically you are expressing oxygen content also. Because the total is 100, oxygen is automatically 33. So it means the content of the other component, oxygen, is 100 minus 67, which is 33%. Okay. So if the components are 2, we use only one element's composition to express the entire material's composition. So if there are n components, we have to express the composition of n minus 1 components. Let's bring some more complexity into the system. Let's add some ice cubes. So now we have 2 phases. What about the chemical composition of these 2 phases? Both are having same chemical composition, 67% of hydrogen. So if 2 phases occur in a material, they can have same chemical composition. In this case, that is true. But is it always the case? The answer is no. Let us see some more examples. So let us consider that water again, single phase. It's a compound. We are now using another word, compound. It is H2O. Now consider a spoon of sugar. It is also a single phase. It's a compound. This is the chemical formula. These two are having fixed composition, meaning you can't have, instead of H2O, H1.9O and call it water. Okay, that's not possible. It's only H2O that can be water. Okay, so that's why we say these things have fixed composition. Right. Now what happens if we mix a spoon of sugar into water? The sugar is nicely dissolved. Can we call it a single phase? Sugar water solution, it is a single phase. Yeah, because the atoms or molecules of sugar, the molecules of sugar are surrounded by H2O molecules and it is nicely dissolved. So it's a atomic level or molecular level dissolution that has happened here. So in that way, it is a solution which is a single phase. What if we add more sugar? Dissolves, even more sugar, it dissolves. So up to what we can keep on adding sugar? This solution can have anything above 0 up to 220 grams of sugar in 100 grams of water. And of course, this is at atmospheric pressure and temperature. So there is a range of composition possible here, meaning 1 gram of sugar or 220 grams of sugar. All of them are called as sugar water solution. Okay? So the solution can have a range of composition. So the compounds are having fixed composition and the solution has a range of composition. So in future we will see that in compounds also there can be a small amount of solubility possible. So that there are some exceptions. We will see about them in future. This is a good enough distinction to have right now between compound and solution. There is of course an idea called chemical order. About that we will see in the next class. Let's add one more spoon of sugar. What will happen? It will precipitate. Because if you add 250 grams of sugar in 100 gram of water, what happens is it crosses the saturation limit. Therefore, the extra sugar that is added will get precipitated. Now what we have is a saturated sugar water solution plus the precipitated sugar. So this can be called as a two-phase system, solution plus compound. Right? Now think about the composition of all this. For composition of water, we are going to say it as 0% sugar. So all of a sudden, instead of calculating percentage of hydrogen, we are saying percentage of sugar. Okay, that's fine, because it's the component that we consider here is not hydrogen but sugar, because the problem here is about sugar water dissolution, not about water formation from hydrogen and oxygen. Therefore, this 0% sugar is the right way to express the composition here for this problem. We will see shortly that components are considered as a matter of convenience. Okay, so this is 0% sugar here is the composition of water. Water has no sugar. Composition of sugar is 100% sugar. Okay, composition of solution at saturation. Okay, what is that? So when it is saturated, we know 220 grams is the maximum sugar that it can hold. So 220 gram is the numerator value. The total is 220 plus 100 gram of water. 220 gram is sugar, 100 gram is water. So the answer is 69% sugar. That is the sugar content. And of course, here we are not counting the number of atoms. We are taking the grams here. So obviously this unit will be different, not atomic percent. This will be mass percent. As I said, we will see about the composition unit separately. So when we add 250 grams of sugar and form two phases, how will we express the composition there? One will be overall composition, which is the composition of the entire vessel. Yeah. That is sugar. In that, sugar is 250 grams. The total is 350 grams, adding the 100 gram of water. So we will get 71% sugar. That is the composition of the entire vessel. But it has two phases inside that. Individual phase compositions we can find out. For the solution which is saturated, we have 69% sugar in that. We have calculated it here. So we have the saturated solution when we have two phases. One phase is a saturated solution. So its composition is 69% sugar. And the compound, which is the precipitated sugar, is nothing but 100% sugar. Okay. So this is the composition of individual phases. So when we have two phases in a material, there are two types of compositions to talk about. First one is the overall composition. Sometimes this overall composition is called as average composition also. I will be using the word overall composition and say this is the composition of the entire vessel. Okay. And the second one is the individual phase compositions. So these are two different compositions expressed for a two-phase material. So if two phases occur in a material, they can also have different compositions. So here we see the saturated solution as a composition which is different from the precipitated sugar. So when we considered the ice and water system, we said two phases are there, but the compositions of both the phases are same. When we had the sugar plus water solution, we had two phases, but both of them have different chemical compositions. So different phases can have same or different chemical compositions. So that is the conclusion about the chemical composition of phases. Right? Let's compile all the understanding that we got about crystal structure and chemical composition of phases. So what you need to know about phases is this: one or more phases make up a material. Each phase is distinct in atomic arrangement and possibly in chemical composition. Okay. So the formal definition is this: phase is a physically distinct and chemically uniform part of a system. For example, physically distinct, you can see that there are two phases. If you see carefully, physically distinct, of course, the physical properties, if we talk about, there are multiple properties to talk about, but you can see that they are physically distinct. The crystal structure and chemistry of them is different, therefore their physical properties are going to be different. Okay. And chemically uniform, this means that chemical composition within a phase is same. Within this black phase, the chemistry will be one and it will be uniform everywhere. Within this white phase, there will be a different chemistry and it will be uniform everywhere. So that is the meaning of a phase being chemically uniform. So with all this understanding, let us look at the significance of microstructure. The structure, which is having these phases and with their different crystal structures and chemical compositions, grain sizes, grain shapes. We didn't talk about these things much, but they are also essential part of microstructure. So all these things we know are going to affect the properties, but what can be used to control them? The processing. Essentially, compositional design is put here as part of processing, but this can even be a separate entity which affects the microstructure. That is how important it is. And this particular course will largely deal with how to select the right composition to get the right microstructure. So chemical composition selection is called as compositional design. Then the other processes that are done to the material, right from its extraction, refining, and casting, welding, forming, heat treatment, and so on. All of them will affect the microstructure, and the microstructure in turn affects the properties. The structural properties, functional properties. The structural properties in the sense the mechanical properties like tensile strength, ductility, toughness, and so on. And the functional properties are like the electronic properties, magnetic properties, optical properties. And of course, there is also the material's response to the environmental factors such as the corrosion, things like that. So they are also properties of materials. So all of them affect the performance of materials. So the microstructure is at the heart of it. What about predicting the microstructure without actually doing the experiment and figuring out the microstructure and see its effect and things like that? How do we predict the microstructure without doing experiments? So now we know that microstructure is controlled by chemical composition and process. How to understand this relation better? So in this course, we will see that microstructure evolution is according to the underlying sciences of thermodynamics and kinetics. So once we understand these sciences, then we can apply them to predict microstructures vis-a-vis the properties. So when it comes to applying these sciences, that is where we are going to use the power of computers. Computational power can be harnessed to apply the sciences of thermodynamics and kinetics to predict microstructures. And this forms the scope of this course, computational thermodynamics and kinetics of materials. So I hope the lecture is useful. Thank you. We will see you in the next class.